Very good morning, everyone. Thank you so much for coming to my talk. I am Selvi Kadirvel. I'm the engineering lead at a startup called Elotl. A quick project background. This is an open source GenAI infra stack built out at Elotl. We are a seed stage startup. We build tools for AI and generic workloads on Kubernetes. We built out Luna, which is an intelligent cluster autoscaler, and Nova, which is a multi-cluster fleet manager. A bit about my background. Prior to Elotl, I was a founding engineer and tech lead at ContainerX. We built out container management platforms. We were acquired by Cisco, and this continued to be built out as a CCP, which is Cisco's container platform, and fronts all of UCS servers as well as Cisco's hyperconverged infrastructure. Prior to this, I was in a field called AI Ops, which is using AI ML techniques for distributed systems performance management. So I worked as a software engineer to auto-scale virtual machines for performance at VMware, and also worked on performance prediction and anomaly detection as part of my PhD thesis. I've been excited to work on this project because it got together my infrastructure as well as my AI/ML expertise together. Okay, I'll start with describing the various characteristics of the AI infrastructure that we targeted and the specific choices that made these characteristics possible. We'll start with the lowest level. GPUs are a critical resource. We were interested in AI inferencing and not training. We wanted to use pre-trained existing large language models. GPUs are expensive, so we needed infrastructure software that could choose cost-effective instance types. Furthermore, even the more affordable GPU types on various major cloud providers are always in limited supply. So in addition to making cost-effective choices, we needed to choose instance types that were available at different points in a day or week. Furthermore, we wanted traditional auto-scaling, which meant that as and when incoming inference workloads increased or decreased, we want to be able to auto-scale our worker nodes on a Kubernetes cluster. We then move on to the data requirements. We wanted to build out a question-answer pipeline for users' private or specialized data that could not be sent out to a third-party AI service provider like OpenAI or Anthropic. This meant that our AI software had to be able to self-host open-source large language models. Furthermore, in order to leverage infrastructure-level scaling, the inference engine also had to be scalable. I'll then go over to the specific choices we made to achieve these characteristics. The bottom two layers are quite obvious, GPU and CPU instance types from cloud providers within the customer's cloud account is what we chose. Kubernetes worked really well for scalable infrastructure. Cluster autoscaler like Elotl's Luna or open source autoscalers like Carpenter work really well to make right-sizing instance size choices as well as autoscaling during day 2 and day 10 operations. In the green blocks are the choices that allowed us to scale the inference engine. We use a project called LLM. This is a project, open source project from University of Berkeley. Their main key highlights are fast inference as well as memory efficient inference, and they have used a distributed inference framework. They use the Ray open source computing framework, which is also a project from University of Berkeley. Its enterprise version is provided by Anyscale. Ray provides both training and inference libraries. VLLM specifically uses the Ray serve component. Above this, in yellow, are the specific open source large language models we worked with. We use Microsoft's Phi-3 model. Even though it's a few billion parameters, around 3 billion parameters, it worked really well for our data sets. We also use Rubra AI, which is from Acorn Labs, thank you. They are open sourced, fine-tuned versions of the Phi-3 model. This allowed for function calling or tool calling from these LLMs. The purple blocks refer to the specific AI pipeline, which we will jump into. Okay, so as soon as we talk about private data, the de facto solution is retrieval augmented generation, which is where we zero in on a small subset of the private data that has relevant information to the user's question. And it works really well for pointed questions. However, we noticed that from our practical experience, we couldn't restrict our end users to only certain types of questions. A number of the questions were of the knowledge aggregation type, which meant that rather than a small sliver of data, there's a wide subset of data that needs to be be used before asking the LLM. This is where text-to-SQL agents come in. In this, the user's natural language question is converted into a semantically correct and syntactically correct SQL query. This is then sent to a SQL database, of course, with restricted read-only permissions. The SQL results are then sent to the LLM to be converted into natural language. So with a combination of RAG agents and text-to-SQL agents, we were able to satisfy all of our end users' question categories. However, the key missing link was a question router. How do we know whether an incoming question is to be answered by the RAG agent or the SQL agent? This is where traditional ML worked really well. We used a text classification model. We played around with a few models, and random forest classifiers worked really well. And that is what was able to kind of link together the two code paths in our pipeline. The data sets that are of interest to us was project management Jira data sets of different internal company databases, as well as customer support Zendesk data set type of data sets. So the end user question comes in, the question router determines which AI path. The data is stored either in a vector database for unstructured data and a SQL database for structured data. The blue box is Phoenix. Phoenix is an open source project from Arise AI, which worked really well out of the box for auto instrumentation. This meant that everything from input tokens, output tokens, inference timings, the specific chunks chosen as part of RAG were all out of the box shown in a nice GUI environment, and that worked really well for us. Okay, so this is the high level of the AI pipeline. We wanted to conclude with some of the lessons learned in this process. Data, real data. AI pipelines are great. They give us a starting structural framework, but without real data, the final solution is completely unusable, not just battle tested. So if you are planning for a GenAI app delivery, make sure you have a sufficient part of your delivery pipeline allocated to real data sets. Data pre-processing, just like a previous speaker talked about, takes a significant amount of time and affects data answer accuracy significantly. Luckily for us, ML engineers and data engineers have been working on this for decades. There's a lot we can learn from and leverage from that field. In our case, a lot of time was spent on field cleanup, choosing metadata for the RAG pipeline, as well as SQL field importance and cleanup. Next comes post-processing of generated responses. There's a lot of chat ML, stands for chat markup language tokens, which get generated as part of different LLMs. These needed quite a bit of cleanup. And only after we started testing with real data set, we were able to identify a large number of hallucination patterns. And once we were able to observe patterns, we were able to clean them up pretty well. Although I'm focusing on real data sets, there's one situation where synthetic data worked really well. It is for question generation. If you talk to your end users and say, hey, give me a list of all types of questions that you'd like this system to answer, they're not going to be able to give you an answer. They'll probably provide you with a small subset, a slightly representative of what they'll eventually use. This is the case where synthetic data set worked really well. This was what we used as training data for our Q&A system with pretty good, about 97% accuracy for the question router. Finally, every one of the block pieces that we showed in the AI pipeline has dozens of tuning parameters. This is a small sample of what was needed. One of the things that we learned was testing on local models, such as OLAML models on your local laptop is great for ironing out Python workflows, but you have to use your actual LLM as soon as possible within your delivery pipeline. We realized that each LLM is a unique beast, and it requires quite a bit of tender loving care to make it perform. So get on to using your final LLMs well before your app delivery deadlines. Finally, do not expect to use your LLM and your inference engine as a black box. There's a lot of parameter tuning that is needed, everything from your KV cache, your model context length, the maximum number of tokens, tensor pipeline parallelism. That is part of your inference engine that become really important. An example of, say, model context length. In theory, the Phi3 model can take, for example, 128K context length. We started with a 4K context length, and we said, hey, this is working really well. If we were able to put in more context, maybe our answers processors will be more accurate, but we're kind of hit back by delayed inference latencies, poor performance, and inference latencies as high as to a few dozens of seconds, which makes your system completely unusable. So we had to do parameter scanning to figure out that optimal golden context length that works well, and good latencies, as well as a reasonable answer accuracy. RAG systems, once again, a lot of parameter tuning available there. Everything from chunk size, if you were to use your VectorDB's API or your LangChain, LangGraph APIs, you will be provided a lot of out-of-the-box parameters, which will most probably not work. So you'll have to spend quite a bit of time to zero in for your specific data sets. So these are some of our lessons learned. That's all I have for today. Our infra stack is fresh out of the oven. It's available at our GitHub repo. Please give it a try for self-hosted large language model question-answer systems. Send me email, connect with me on LinkedIn. Happy to help you make it work for your environment. And thank you. I'm happy to take any questions if you have any.
Thank you. Thank you very much. So don't. If you have a question, just go to the microphone. I see one there. Yeah, go ahead.
Hello. Great talk. Thank you very much. Very inspiring. I would have two questions. The first one being a little bit controversial, being here at KubeCon. Why Kubernetes? Why not a different scheduler? And the second question, you mentioned about tool calling, and I forgot Rubri.
Rubra.
Yeah. My question is, are you using model contracts protocol at all, and does that work?
Sure. First question, Kubernetes scalability was an important requirement for us, and Kubernetes provides it out of the box for us. We built cluster autoscalers, so it was a match made in heaven. The distributed inference engines worked great. For example, we would start with the cheapest AWS EKS instances. We could quickly kind of scale it up to, say, 4 GPUs. We had improvement in inference times from a few dozens of seconds to a few seconds. So the scalability of all of the pieces worked really well together, which is why we went with Kubernetes. With respect to tool calling, no, we do not use the model control protocol. These fine-tuned and the foundational models worked really well for us.
Thank you very much.
Thank you for the question.
Thank you. There's one more question, and that's it after. Yeah.
Okay. Thank you very much for the talk. I really did enjoy it. I have a question on the data processing. What was your tech stack? How did you actually process it? Did you use Go? And if so, was it like Go routines? Give us a little insight.
Sure. It was a lot of Python processing. Everything was Python. We were a Go tech stack, but as soon as we moved into the, going up the GenAI stack, Python was what allowed us to provide us with a lot of the modules we needed for cleanup, pre-processing and cleanup.
Got it. Thank you.
Thank you.
Thank you very much. Let's thank Selvi again. Thank you.